Hello, students! Today we are going to understand a very interesting topic in chemistry. We're going to explore the world of ideal and non-ideal solutions. So let's start with a little puzzle, something you might have even seen in your chemistry lab. Have you ever wondered why, when you mix two simple, clear liquids, the container can sometimes become quite warm? Well, take the case of mixing acetone and chloroform. Something very peculiar happens. Not only is heat released, making the container warm, but the total volume of the mixture actually shrinks. That's right. If you mix 50 milliliters of acetone and 50 milliliters of chloroform, you will not get 100 milliliters. You'll get something less. So how is this even possible? To understand this puzzle, we need to look at the difference between a perfect, theoretical mixture, what we call an ideal solution, and what happens in reality with non-ideal solutions. The ideal solution is our baseline, our perfect model to start from. Okay, let's dive into this. First, we need to properly understand the ideal case. This is our theoretical starting point. Imagine you have a bag of red balls and a bag of blue balls. Now, these balls are identical in every way except their color. Same size, same material. When you mix them, they mix completely randomly. A red ball doesn't care if it's next to another red ball or a blue ball. This is the core idea of an ideal solution. So the crucial point, and the definition for your exams, is this. In an ideal solution, the interactions between all the molecules are identical. This means the force between two solute molecules, two solvent molecules, or between a solute and a solvent molecule are all exactly the same. They are, you could say, completely indifferent to who their neighbors are. Now, this indifference has two very important consequences. First, the enthalpy of mixing, which we write as delta H mix, is 0. This simply means that no heat is released or absorbed during the mixing process. The temperature does not change. Second, the volume of mixing, delta V mix, is also 0. This means the final volume is exactly the sum of the initial volumes. 50 milliliters plus 50 milliliters will give you exactly 100 milliliters. So, that is the ideal case. But in reality, molecules often do have preferences. They are not always indifferent. This leads us to the much more common and interesting category of non-ideal solutions. You see, most real solutions are non-ideal. And the reason is simple. The forces of attraction between the unlike molecules, that is A and B, are different from the forces between the like molecules, AA or BB. This difference in forces can lead to two types of deviations from ideal behavior. If the new AB interactions are weaker than the original AA and BB interactions, the molecules find it easier to escape into the vapor phase. This leads to a higher vapor pressure than predicted, and the process absorbs heat, so delta H is positive. We call this a positive deviation. On the other hand, if the new AB interactions are stronger, the molecules are held together more tightly. This lowers the vapor pressure, and because a more stable bond is formed, heat is released, making delta H negative. This is called a negative deviation. To understand this better, let's try to picture the molecules themselves and see what is actually happening. First, let us look at a nearly ideal mixture. A good example is mixing two similar liquids, hexane and heptane. Now, hexane and heptane are very similar molecules. They are both nonpolar, and the only forces between them are weak London dispersion forces. Because they are so similar, the forces between two hexane molecules, two heptane molecules, or a hexane and a heptane molecule are all almost equal. As a result, they mix perfectly and randomly, just like our colored balls. Now, let's return to our original puzzle with acetone and chloroform. This is a classic example of a non-ideal solution showing a strong negative deviation. Here, the situation is completely different. When you mix acetone and chloroform, the molecules form new, strong hydrogen bonds with each other. This new attraction between an acetone molecule and a chloroform molecule is much, much stronger than the forces between two acetone molecules or two chloroform molecules. This strong pull is what pulls the molecules closer together, causing the volume to shrink. And because a stronger, more stable bond is formed, energy is released in the form of heat. So you might be thinking, why do we care so much about this distinction between ideal and non-ideal? Well, it turns out this concept has very important practical applications in the real world. This concept is not just theory for your textbook. Understanding this non-ideal behavior allows chemists and engineers to perform separations of liquids on a huge industrial scale that would otherwise be impossible. A key example is in making fuel-grade ethanol. You see, ethanol and water form a non-ideal mixture called an azeotrope. This special mixture boils at a constant composition, which means you cannot separate them beyond about 95% purity using normal distillation. So, to get 99% plus pure ethanol, industries use a clever process called azeotropic distillation. They add a third component which breaks this azeotrope, allowing them to achieve the high purity needed for fuel. All right, let's do a very quick recap of the main ideas you need to remember for your exams. First, remember the core idea. Ideal solutions are the simple theory, the perfect baseline. Non-ideal solutions, where molecules have preferential interactions, describe how most solutions actually behave in reality. Second, keep that simple analogy in your mind. Are the particles indifferent to each other, like identical balls? Or do they have a preference, like mixing balls that are either sticky and attract each other strongly, or repellent and try to stay apart? And finally, connect it back to the real-world example we started with. The strong attraction in non-ideal solutions, like in acetone and chloroform, can release a lot of energy, which we can actually feel as heat. If you just keep these three things in mind, the core idea, the mental picture of the balls, and one key example, like acetone chloroform, you will be very well prepared to answer any question on this topic. It will feel much lighter. You know, this idea of a perfect model versus a more complex reality is common throughout science, so I will leave you with a question to think about. What other perfect theories in science can you think of that have fascinating real-world exceptions which actually reveal a deeper truth?